So now that we've talked about linear independence and span, we can talk about having a basis for a set of vectors, for a vector space. So the idea is we want to go ahead and describe a vector space in terms of some very much smaller subset. This set can be considered to be kind of our building blocks that we're going to use to build any vector from the vector space. So recall that a vector space can be written as a span of vectors, and sometimes when we compute this span of vectors, we saw kind of in the last example of the previous video, we can write it as an even smaller set of vectors. What that means is that the vector space can be described with an even smaller set of vectors than before, and when this happens, the larger set that we had is going to be a set of linearly dependent vectors. So our main goal is to find a spanning set that's big enough to describe all of our elements, but not so big that we have kind of repetition in the elements. So given a vector space V, we call the B here, the script B, which is going to be V1 through Vn, the basis of a vector space V, if and only if it satisfies the following conditions. First, the span of that basis, that set, has to be equal to the vector space, and B has to be linearly independent. So think of it this way. It's kind of like Goldilocks. We want our set to be big enough so we can represent any vector in V, but not so big that we have repetition or redundancy in our set B. Alright, so the standard basis for R3 is going to be the set 1, 0, 0, 0, 1, 0, 0, 0, 1. So let's talk about why this is the case. When we look at R3, we know that R3 is the set of all x, y, z, such that x, y, and z are elements of the real numbers. And so we can take and break this down to being x times the vector 1, 0, 0 plus y times the vector 0, 1, 0 plus z times the vector 0, 0, 1, where x, y, and z are in the real numbers. And so this then lets us see that this is R3 can be written as the span of 1, 0, 0, 0, 1, 0, and 0, 0, 1. So that checks off the first thing. First thing then is that we have that our vector space is the span of these three vectors. The next thing we would need to show is that they're linearly independent. So this is the first part. And our second part will be to show linear independence. What that means is that if I take some alpha 1 times 1, 0, 0 plus alpha 2 times 0, 1, 0 plus alpha 3 times 0, 0, 1, I should only get 0, 0, 0 if alpha 1, alpha 2, and alpha 3 are all equal to 0. So let's add these up and check. We get alpha 1, alpha 2, alpha 3 has to be equal to 0, 0, 0. So since alpha 1 equals 0, alpha 2 equals 0, and alpha 3 equals 0 is the only solution to this linear dependence relation, our set is linearly independent. Okay, so great. So we've got a set that spans, the span of that set is R3, and it's linearly independent. And so by these two combined, we have a basis for R3. Okay, great. So, we've got our basis. And so, just a little bit of notation. The standard basis is something that's actually pretty intuitive to kind of build and come up with on your own. So because it's so often used, there's sometimes going to be special notation for it. Sometimes it'll be E1, E2, and E3, and they're going to denote basically the vector that has a 1 in the first position or second position or third position and zeros everywhere else. And so if you ever expanded this to say Rn, say R5, E1 through En is going to just denote that the subscript is where the 1 shows up in that vector and there are zeros everywhere else. It might come up in the WebAssign, and that's why I'm making sure to mention it. So let's show that another basis for R3 is going to be this set B of 2, 0, 1, 1, 1, 0, and 0, 0, 1. So remember, we have 2 steps here. One is to show that the span of this B is equal to R3, and the other is to show that B is linearly independent. In the future, you might see me just write this as lin ind. So just keeping that in mind. All right, so let's show that the span of these vectors is equal to R3. So we need to have an arbitrary representative R3. We're going to just pick an x, y, z here. So we have alpha 1 times 2, 0, 1 plus alpha 2 times 1, 1, 0 plus alpha 3 times 0, 0, 1, and set this equal to some x, y, z. Then we should be able to go ahead and create a matrix for this. So if you're not sure how to jump from here to a matrix, ask about it in the discussion boards and we can talk about it. But the matrix that we should get here is 2, 1, 0, x, 0, 1, 0, y, and 1, 0, 1, z. Now, when we get the reduced row echelon form of this, we should know how to do this through the use of octave. But if you're having trouble, again, ask, and I'll be happy to share. 1, 0, 0, x minus y over 2, 0, 1, 0, y, and 0, 0, 1, negative x over 2 plus y over 2 plus z. So here, how many solutions did we get? If you answered 1, that would be correct. So since we have at least one solution, the span B is equal to R3. And so this just comes from our discussions about span, the span of a set and how to get a vector space. So since we got a solution here, we're able to say that this set is a spanning set for R3. And so now, for linear independence, what we want to do is we're doing the same thing, alpha 1 times 2, 0, 1, plus alpha 2 times 1, 1, 0, plus alpha 3 times 0, 0, 1. But now we're setting it equal to 0, 0, 0. Now remember, in order for us to end up with something that is linearly independent, we need to make sure we only get one solution to this problem. So now we'll set up a very similar matrix, 2, 1, 0, 0, 0, 1, 0, 0, and 1, 0, 1, 0. And when we go to get the reduced row echelon form of this matrix, we'll end up getting 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0. And so here, since we have only one solution, B is linearly, said I'd shorthand it this time, independent. Okay, and then combining it all, since span of B equals R3 and B is linearly independent, B is a basis for R3. So this is what we were looking for. We wanted to show both of these things so that way we could show that we did have a basis for R3. So this was our big thing that we wanted. And so with it being a basis, we could use those three vectors that we had before in order to write and describe any of the other vectors in R3. Okay, so now let's talk about polynomials. So the standard basis for P2 is this set S, which is x squared, x, and 1. We want to show that S is a basis for P2. Remember that P2 is going to be the set of all ax squared plus bx plus c, such that a, b, and c are in the real numbers. And so here we already know that this is something that can be written as the span of x squared, x, and 1. So just to summarize, we know that the span of S equals P2. So we did that part already. We need to show that S is linearly independent. And if we've done that, then we'll have done the two things necessary to show that this is indeed going to be a basis. So let's take a look. If we look at taking alpha 1 x squared plus alpha 2 x plus alpha 3 and setting it equal to 0. So remember, this is our linear independence, or linear dependence relationship. Here, remember, what we're doing is we're going to be comparing the coefficients for x squared, x, and the constant portion on either side. And so here we get that alpha 1 is going to be equal to 0, alpha 2 is going to be equal to 0, and alpha 3 is going to be equal to 0. So since this is the only solution, S is linearly independent. Okay, and so since we know that the span of S is P2 and S is linearly independent, we can combine those things to say that S is a basis for P2. All right, so let's look at another example. So let's say we wanted to look at 1 x squared plus x and x squared. If we took a look at this set, in the last video we showed that this was linearly independent. So here we know that B is linearly independent. We did this before. We need to show that the span of B is equal to P2. So here, in order to show that, what we're doing is we're going to take alpha 1 times our first vector plus alpha 2 times our second vector, x plus x squared, plus alpha 3 times x squared. We're going to set that equal to an arbitrary representative from P2, so sum ax squared plus bx plus c. So again, we can distribute the alpha 2 through, and so we'll get alpha 1 plus alpha 2x plus alpha 2x squared plus alpha 3x squared to get ax squared plus bx plus c. And so if we rewrite these a little bit, we get alpha 2 plus alpha 3 x squared plus alpha 2x plus alpha 1 equals ax squared plus bx plus c. And so I'm going to take a moment to pause. I think in the last video we had these in the reverse order, but right now the order they're in is not important, just the fact that we have them all. And so comparing then the coefficients for x squared, x, and the constant, we end up with the following system of equations. Alpha 2 plus alpha 3 equals a, alpha 2 equals b, and alpha 1 equals c. And so this gives us the matrix 0, 1, 1, a, 0, 1, 0, b, and 1, 0, 0, c. And if we obtain the reduced row echelon form of this, we end up getting 1, 0, 0, c, 0, 1, 0, b, and 0, 0, 1, a minus b. And so, since we have at least one solution, the span of B equals P2. So there's then another thing where we've now shown that B is linearly independent and the span of B is equal to P2. So if we combine those things, that tells us that this set B is a basis for P2. All right, so notice that something interesting happened in the last 4 examples. We saw 2 examples where we had basis of a vector, different bases of a vector space that had the same number of elements. That is, when we looked at R3 and we had 2 different bases for those, they both had 3 elements in them. And when we looked at P2 and both of those bases, both of those had 3 elements as well. And you might want to ask the question and wonder, that's always going to be true? And the answer is yes. So let's see that we have a vector space going from with 2 different bases. So B1, which has n elements, V1 through Vn, and B2, which has m elements, U1 through Um. Then the number of elements n in B1 has to be the same as the number of elements m in B2. And so that is n has to be equal to m. There's a bit of a nice long proof here on page, looks like 68, that kind of explains the reasoning behind why this ends up being. For now, I'm going to let you guys read that on your own. We're not going to be too focused on the proof bit there, and it also trickles a little bit on to the next page. All right, so there are a couple of questions on this page that I want you guys to kind of think about as we go. So before we look at this example, I want you to take a minute to kind of pause and ask, is this a basis for R3? All right, now you could have done this one of 2 ways. You could have went ahead and checked to see if it was a spanning set, if it was linearly independent, or you could just use that theorem we just found and notice that when we had different bases for R3, they had 3 vectors in them. So we know bases for R3 have 3 elements. And this has 4. So no, this cannot be a basis for R3. There are too many elements. It's going to fail at least one of our things. And because we have a specific number of elements in a basis, and that's unique to the vector space, we can give that a name. So given a vector space V whose basis B has n elements, we say that the dimension of V is going to be n, the number of elements in B. Sometimes we'll say that V is n-dimensional. So based on the examples we've seen so far, we can see that both R3 and P2 are going to be things that are 3-dimensional. Notice this is a little bit of a pitfall with polynomials because we have to worry about the highest power being that subscript, but also the constant term. Sometimes people will at first mistake this for being something that's 2-dimensional, and if you write it out and kind of look at it, play around with it, you'll see that this is 3-dimensional. And we kind of showed that over the last couple of examples as well. So note, what we see is that in order to find the dimension of a vector space, we need to find the basis and count how many elements it has. This can also help immediately check whether or not a set of vectors is a basis. So note that if we look at P4, this is the set of all ax to the 4th plus bx cubed plus cx squared plus dx plus e, such that a, b, c, d, and e are in the real numbers. And this is the span of x to the 4th, x cubed, x squared, x, and 1. So because of this, its dimension is 5. So we know that any set that doesn't have exactly 5 vectors cannot be a basis for P4. Now note that just because we have something that has 5 vectors doesn't mean it will be a basis for P4. So, for example, if we have a set x to the 4th, 2x to the 4th, 3x to the 4th, 4x to the 4th, and 5x to the 4th, this is not a basis for P4. So just because we have 5 vectors doesn't mean we're a basis. We need to also verify that we are a spanning set and are linearly independent. So bases are not going to be unique, but we often want to try to find the easiest basis or set of building blocks we can have. So if we're looking at the standard basis for M2 by 2, this should be, if we look at M2 by 2 and use this definition, where we have the set of all A, B, C, D, such that A, B, C, and D are in the real numbers, this is just the set A times 1, 0, 0, 0, plus B times 0, 1, 0, 0, plus C times 0, 0, 1, 0, plus D times 0, 0, 0, 1, such that A, B, C, and D are elements of the real numbers. So, taking a look at this then, this is just the span of 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So our easiest way of describing this set would be by using these building blocks that kind of just let us take and isolate a 1 in each of the positions at a time. So here, our easiest basis, if we say this was our set B, this would be the standard basis for M2 by 2. All right, so we don't always have to worry about just bases for, say, bigger vector spaces. Sometimes we need to worry about them for subspaces as well. So let's see an example of that. So say we've got a set of vectors, x, y, z, such that x plus y plus z equals 0, 2x plus y minus 4z equals 0, and 3x plus 2y minus 3z equals 0. We want to find the dimension for v, so first we need to write v as the span of vectors. And so here we start off with our equations, we use a matrix, we do some row reduction, and we see here that we get the set of all x minus 5z equals 0, and y plus 6z equals 0. Notice here that because we have a column that doesn't have a leading term, z is free, and so we end up getting x equals 5z, y equals negative 6z, and z is free. And so to get that, what we'll see then is we have the set v of all x, y, and z such that x equals 5z, y equals negative 6z, and z is in the real numbers with it being free. And so we've got the set of all 5z, negative 6z, z, such that z is an element which can be also written as z times 5, negative 6, 1, such that z is an element of the real numbers. And so that means that it is the span of 5, negative 6, 1. So here we're saying that the set 5, negative 6, 1 is a spanning set for v. So then our b, our potential basis, for v is going to be the set of 5, negative 6, 1 as a vector. Now I say potential basis because we've only done the spanning set part. We also need to show it's linearly independent. So this was spanning, or span of b equals v, and 2, we need to show b is linearly independent. So we need to do that. So if we take alpha 1 times 5, negative 6, 1, and set that equal to the vector 0, 0, 0, what that tells us then is that 5 alpha 1 equals 0, negative 6 alpha 1 equals 0, and 1 alpha 1 equals 0, which in the end tells us that alpha 1 has to be equal to 0. So since alpha 1 equals 0 is the only solution, b is linearly independent. And so now, between 1 and 2 being satisfied, b is a basis for v. Now, our original question was we wanted to know what the dimension of v was, and so since we now have a basis, all we have to do is count how many elements are in that basis. And as you can see, we have only a single element. So then the dimension of v is just 1.